everyone, welcome back. We're moving on to a new topic. The new topic is numerical differentiation. We're going to do 3 videos of numerical differentiation. Today's video is going to be theoretical only. We're going to cover these 3 methods, forward, backward, and central difference. The next video is going to be on some tweaks to this central difference approach so that we can get some very specific results. And then we'll be talking about higher order differentiation. So that's video 2. And then video 3 is going to be implementation. So we will see all of these all these 3 methods put into practice, and we'll see the code running. So here's how we want to start. Let's start by introducing this topic of numerical differentiation. Then we're going to go through these 3 methods. The best method is the central difference. So we're going to finish with the pseudocode for the central difference method. What do we mean when we say numerical differentiation? We know that we can do analytical differentiation. We know from calculus if I give you some function explicitly, f of x, something small to begin, 3x squared, we know that we can find the slope of this, the derivative of this, right? We can differentiate it. Clearly f prime of x is going to be 6 times x. What if this is a very complicated function? What if f of x is not something so small, 3x squared? What if we did sine of cosine squared of x to the 3/5? Okay, we could do something even more complicated, but we can absolutely find the derivative of this. We can chain rule and product rule our way through basically anything. If you were given a function explicitly, you can find the derivative of that function. What we're about here with the numerical differentiation, we're addressing the problem of what if you do not have the function explicitly? What if, instead, what if all you have is the data? So for example, I've put some data here. We have 4 x values, and then I have the f of x that goes with it. Now, you might be able to just look at this and tell that our f of x is x cubed. So all I've done is I've just taken this function f of x and I put some values into it. Again though, what if we don't explicitly have that function? What if this is data from a set of sensors? What if you're tracking an object, and this could be perhaps position, and we want to know how fast the object is moving, which means we would like to differentiate it, right, to find the speed, to find the change. So all we have to work with are the data points. So let's start graphically, and let's see if there, just kind of by intuition, if there's something that we can come up with to find the derivative. So here's f of x on the vertical, here is x on the horizontal. You can see our data points are 1, 1.5, 2, 2.5. And then our y values are going to range from 1 all the way up to about 15.5. So let's say 4, 8, 12, 16. Okay. Our data points then are going to fall, let's see, 1, 1, 1.5, a little under 4, 2, 8, and then 2.5, almost 16. Okay. So we can see that this this function, right, this function is trending up, which again, we know what the explicit function is, x cubed, which that makes sense. So all we have are these data points. We don't have any information about the points in between, right? And what we are attempting to find, what we want out of this, is we want f prime, right? We want the slope. I'm saying that we are going to numerically differentiate this data, which means we want f prime. Now, what can we do to find the slopes at certain points? Well, one thing we could do is we could pick 2 points. We could say, let's say we're trying to find the slope here at x equals 2. If I want to find the slope at x equals 2, There's the data point. What if we take the data point that comes after it? What if we take, we say x is equal to 2.5. Here we go, we're talking about this data point here. And how could we calculate the slope? We could do rise over run, right? We could say, what's the change in these? So we would take f, there we go, f of 2.5, and we can subtract f of 2, and we can divide by the difference. And in this case, the difference is 0.5. We went from 2 to 2.5, 0.5. If you calculate this, I've already got those numbers crunched, you will get 15.25. And what I'm saying for the f of 2.5, again, we have those numbers, right? I'm giving you those numbers. So you just take those numbers, you put them in here, divide by 1/2, and you'll get 15.25. That's choosing the data point in front. We could have just as easily chosen the data point behind it. We could have selected this data point. We could take the same approach, rise over run. If we do, we're going to get these numbers. We're going to take f of 2, and we're going to subtract f of 1.5, and we're going to divide by 0.5. And this time when you get that answer, when you calculate this, you're going to get 9.25. So here's just two kind of intuitive approaches, looking at it and just saying, hey, take that point and that point. These were the numbers we calculated, 15.25, 9.25. Clearly there's a big difference in these numbers. So we can see that this kind of just intuitive approach, it's very sensitive as to which one of these you selected. But what is the actual answer? Again, we know the function, and if f of x is x cubed, then f prime of x is going to be 3x squared, and we wanted the slope at 0.2, x equals 2. So you put 2 in, so f prime of 2 then is going to be 3x squared, so that's 3 times 4, so that is 12. So the answer is 12, and our two methods, right, our first two approaches gave us 15.25, and then 9.25. So these are not great. You could try some kind of interpolation. You could attempt to maybe take an average or something like that. We would really like we'd really like a more formal method than just saying take the average of these and hope for the best, right? So this is leading us now into our three methods for the day. There's forward difference, backwards difference, central difference. So let's take each of those one at a time. Let's start with the forward difference. What we're going to find is the forward difference is actually the first of those two graphical approaches that we attempted. Again, the kind of intuitive approach of just taking the difference between 2 points. Now, what we're about to do is going to seem like overkill, but I assure you it's going to come in handy later. So let's see if we can come up with a formal declaration or formal definition of what it was that we did just a moment ago. We want to evaluate the slope at f of x, and we're going to consider our information at some point in the future. So we know f of x, and we can move to some second point in the future, f of x plus h. So this is where the term forward difference comes from. What we're going to do is we're going to take f of x plus h. We're going to do a Taylor series expansion on this term. So remember, the Taylor series is an infinite series, so it's actually equals here. In a moment, we're going to end up truncating the series, and it's going to make it an approximation. But for now, it's equal. So the Taylor series is this. It's f of x plus h times f prime of x plus h squared over 2 factorial multiplied by f double prime of x. I'm going to do one more. This is now h cubed over 3 factorial multiplied by f triple prime of x plus, and I'm just going to say plus dot dot dot. So this series goes on onto infinity. Now, what if we're going to take this, and clearly we can't include all of the terms. Let's actually truncate this, and we're going to truncate it here after this first derivative term. So I'm going to say, I'm going to change this equals to approximate, and we're going to truncate the series right here. So all we're left now with are these three terms, and then we've truncated those. So what this tells us, f of x is equal to, f of x plus h equal to, approximately equal to f of x plus h times f prime of x. Now, remember what it is we're attempting to do here. We're attempting to find the derivative, right? We want to numerically differentiate it. And in this expression, we have the derivative. The derivative is f prime, right? So we can take this equation and we can just rearrange it. We can solve for f prime. F prime of x is going to equal, well, what do we need to do? We need to move f of x to the left-hand side, and we need to divide by h. So this is approximately equal to f of x plus h minus f of x, and it's this divided by h. Now, this might look familiar. This is this ends up simplifying down to a definition of derivative, right? If we took this and we did a limit on it, this would give us the instantaneous derivative, right? Unfortunately, we don't have infinite number of data points. We have fixed number of data points, right? We're performing this process numerically. Now, if we were to do this for the numerical example that we did a moment ago, here's what we would have. We would have, and we're going to say f prime at 2. We're still going to chase the slope here at 2. So again, this is approximate, but this is going to equal f of 2.5 minus f of 2, and then we were dividing by h. H on that problem was 0.5, and if you calculate this, you get 15.25. Again, this was that first kind of naive approach that we did, just looking at it graphically. So this is called forward difference method. Imagine that you have a whole bunch of data sets, right? Or you have a data set with a whole bunch of data points in it. I'm going to erase this right-hand side. Let's say that you have x and f of x, and you have all of these data points. And on and on and on it goes. Okay. Consider if you want to use the forward difference method. In this case, we solved for the slope at x equals 2. It required us to use the point in front of it. So if we wanted the slope at the very first term, it would require that we use the first term and the term in front of it. If we wanted the slope on the second term, it would require that we use the second term and the third term. If we wanted let's say this is the 10th, right? This is the 10th data point. It's going to require the 10th f of x10, and it's also going to require the 11th. Now, this is important because what happens when you get all the way to the last data point? What if your data set has 1,000 measurements in it, and you get all the way down to the 1,000th measurement? Here's the 1,000th measurement. There's some number here. It's 1,000. X equals 1,000, and this is equal to 47. Sure. We want to know what the slope is at this 1,000th data point. Unfortunately, using forward difference, we can't find it because there is no future data point for us to call upon. So, number one, forward difference method. It's a very simple implementation, but it doesn't give you a fairly accurate answer, right? I erased it, but 15.25 is significantly different than 12. So it's not particularly accurate. It also has this limitation in that you cannot use it to find certain data points, right? We can't use it to find the slope at the end. It always requires more data in order to find slopes in the past. So there's our forward difference. Let's change gears. Let's talk about the next method, backward difference. as we saw with the forward difference, we still want to find f prime of x, right? We still want f prime of x. And this time we're going to use it, we're going to find it by evaluating f of x. And instead of doing x plus h, we're going to go backwards. We're going to do x minus h. So we still have these 2 points, and we want to find the slope at x. So we're still going to do a Taylor series expansion. Let's say f of x minus h. It's minus h this time. Here is our Taylor series expansion. It is f of x minus h f prime of x plus h squared over 2 factorial f double prime x minus h cubed 3 factorial f triple prime x, and then plus dot dot dot, all the higher order terms. Now we're going to do what we did last time. We're going to truncate this infinite series. We're going to cut these terms off here. And then since we truncated the series, this also becomes an approximation. This is approximately equal to. Now, we still want to find f prime. Here's f prime. So take this equation and solve for f prime. So we have f prime of x. If you move f of x to the other side, notice that the f prime is itself negative, so we need to multiply the whole thing by -1. So we're going to have f of x minus f of x minus h. Notice that these two are reversed order. Again, multiply by -1. And then we're going to divide by h. Now, this is the other approach that we did. The other intuitive approach where we just took the point behind it, right? So we've already done this calculation. This is f of 2, and we're subtracting f of 1.5, and we are subtracting by 0.5. And in that numerical example we did, this gave us 9.25, which again, simple implementation, but not particularly accurate, right? Okay. What are the limitations of this method? We saw there was a big limitation on forward difference where you couldn't select the final data point. Notice in this method, we're not going to be able to select the first data point this time. If, erase the right side, if here, again, here's our data points, x and f of x. We have a whole table of these. We can use backwards difference to find the slope at the end this time. I could find the slope for the last one using these two, f of the last one and the one before it, right? F of 2 and then f of 1.5. The limitation here, though, is that we cannot use it to find the slope at the first point. So you could use forward difference to find the slope at the first point. You could use backward difference to find the slope at the last point. Once we get through all the videos on this topic, we're actually going to do neither of those things. But let's keep moving on. Let's move on to the next method. So we've done forward and backward difference. Let's move on to the third method for the day, central difference. This time, we're not going to use f of x and the one before it, f of x and the one behind it. This time, we're going to use f of x plus h, the point in front, and we're going to use f of x minus h. So we're going to use the point in front and the point behind it. We're going to do some Taylor series expansions, right? I'm going to do the expansions for f of x plus h and f of x minus h. I've gone ahead and written the expansions. Here's the expansion for f of x plus h, expansion for f of x minus h. These are the same expansions from the previous discussion, so you should already have these in your notes. I labeled the one on top equation 1 and the one on bottom equation 2. Now, remember these infinite series, they are exact. If you include all the infinitely many terms, you get the correct answer, right? This is an exact. We replaced this with an approximation because we truncated this series, right? And we cut off some of these higher order terms. What that means is when we use the forward difference and the backward difference to calculate the numbers and we got the wrong answer. We got something close, but we got the wrong answer. We got the wrong answer. The error in that answer comes from the truncation of these terms, right? The more of these higher order terms that you include, the more correct, the more accurate your answer is. Now, what we're going to do is we're going to attempt to recover the slope, right? That's what we're going for here. We want to take the derivative. We're going to attempt to recover f prime using both of these. And the clever point on this one is to avoid truncating the higher order terms as much as possible. If you can truncate even higher, right, and you can keep some of the lower terms, then that will give you a more accurate answer. So what we're going to do is we're actually going to take equation number 1, and we're going to subtract from it equation number 2. If we do this, here's what we get. We get f of x plus h minus f of x minus h. Okay, and I'm gonna say equals because we're not going to truncate yet. Clearly, this is what's happening on the left-hand side. If I take equation number 1 and I subtract equation number 2, then the left-hand side is x plus h minus x minus h. Good. Now, what happens to these higher, the terms on the right-hand side? Well, we're subtracting these two. So that would be f of x minus f of x, right? So the f of x's will cancel. Next, we're going to have h f prime x minus the negative h f prime x. That's going to give us 2h f prime x. What happens to these terms, the h squared terms? Well, these are both positive and they're the same, so when you subtract them, these also go to 0. We can see that the odd terms are going to add. So here is 2 times h cubed, 3 factorial f triple prime x, and then I'm going to say plus dot dot dot. And there's a pattern. We can clearly observe the pattern that's arising out of this. Let's call this one an odd term because this is the first derivative. So the odd terms stay and they double. And then the even terms, right, the 0th derivative, the 2nd derivative, the 4th derivative, and on down the line, these are all going to, they're all going to equal 0. They're going to cancel, right, because we're subtracting. If we want to truncate this series now, where do we truncate it? Well, we can truncate it right at this point. Now, if we truncate it at this point, what higher order terms are we ignoring? We're cutting out the 3rd derivative at this point, right? I don't have to cut out the 2nd derivative because the 2nd derivative actually went to 0, which means you're truncating at a higher order, right? On the previous methods, we had to exclude the f double prime. At this point, the f double prime is actually included. It just happens to equal 0, so we're truncating the 3rd derivative and higher. So that means that the error in this approach should be less. Now, we want to use this method, and we want to solve again. We want to solve for f prime. So I'm going to erase the top part, and let's solve for f prime. And since we're doing the truncation, this becomes approximate. How are we going to solve for f prime? Well, it's basically already set up, right? Here's f prime. You just divide by 2h. So f prime of x is going to equal the left-hand side, f of x plus h minus f of x minus h, and this is all divided by 2 times h. Good. So this is the central difference scheme. Let's check how accurate it is. I'm going to erase now the bottom, and let's use those numbers from the numerical example that we did. We want f prime at 2. That means we're taking f of, now what does this mean, x plus h? We're looking x is equal to 2, h is 0.5, so this is f of 2.5, minus, this one is going to be f of 1.5, divided by, again, h is 1/2, so 2h is 1. If you make this calculation, what you will get is 12.25. Now, what was the actual answer? We said f of x was x cubed, so f prime of x was 3x squared, and at number 2, f prime of 2 would have been 12, right? It would have been 3 multiplied by 4. So the correct answer is 12. Central difference scheme gave us 12.25. Significantly better than forward difference or backwards difference, right? Okay. So last comments on this one, and this will be it for the day. What are the limitations on the central difference scheme? Well, recognize that it requires, in order to find the slope at x, you use the data point ahead of it and the data point behind it, which means you cannot use central difference for the first or the last data points, right? Because if you're at the first, there is no data point before it, and if you're at the last, there's no data point after it. So what we need then is we need some way to accurately calculate first and last points. We don't want to use the forward difference and backwards difference because they're inaccurate. This method, the central difference, is much more accurate, and it's more accurate because we're truncating at a higher order term, right? We're cutting out the third derivative. So next time when we come back, we're going to talk about how to deal with those specific problems. How do you calculate, numerically calculate the derivative on the first and last points? And also, this is the first derivative only. Next time, we're also going to talk about how to calculate f double prime of x. So if your function, you could say like this is position, so the first derivative would be speed or velocity. Next time we'll talk about how to numerically calculate the acceleration. Let's talk about the pseudocode for the central difference method, and we'll get out of here for the day. Number 1. Now, central difference, numerical differentiation. Again, this is usually done on data sets or sensors or measurements or something like that. So number 1, I'm gonna put kind of a general expression here. I'm gonna say either load or generate, synthesize, something like that. You need to load or generate your data because again, this method is applied to data. Number 2, from the data, calculate h, and h is going to equal x2 minus x1. Now, there is an assumption built into this part. The assumption is that if you're going to do this kind of ahead of time, before the whole algorithm kicks in, that means we're assuming that your measurements or your data points, they happen at equally spaced out moments in time, right? If there's a certain amount of time between x2 and x1, at this point, we're assuming that it's the same amount of time between x3 and x2, x4 to x3, etc. You can adjust this approach if you're taking measurements at irregular intervals, but I'm not going to make you do that. So for now, we're just going to say you calculate a single h, and we're going to assume that that is constant for your data set. 3. Iterate across all points. And I'm actually going to put a little, this is kind of a comment. We'll come back to this in a second. I'm going to put a little asterisk on the points part. So iterate across all points using, and I'm going to use the central difference method, which is f prime of x is equal to f of x plus h plus f of x minus h, all divided by 2h. So again, this was that central difference scheme that we came up with. And number 4, so we have not done actually the details for number 4 yet, but I'm going to go ahead and put it in. Number 4 is use specific formulation. Sorry, the words are kind of running together. Use specific formulation for first and last points. So this first and last points, that was my comment about iterating across all points. Just remember, using central difference, you can only calculate it for the data points in the middle. Central difference cannot be used for first and last points. We're going to cover this part in the next videos. I'm going to talk about how to get the slopes at the first and last points with the exact same accuracy as the central difference. Okay, there's your pseudocode. You've got the theory. You have to go write some scripts, right, to solve this, to use these to solve some lab problems. You know the drill. If something comes up, let me or the TA know. Otherwise, best of luck. I'll see you next time.